This is a further math question on summation series, winter 20, variant 1-2. In the first part, we have to show that this thing is equal using this expansion. This expansion is the expansion of a plus b, a minus b equals to a square minus b square. Now in this, we can take the denominator to the other side. So on the other side, we have this minus x power n minus x power 2n plus 1 under root is already there, and then this denominator goes to the other side and we write x power n minus root x power 2n plus 1. Now if we take minus sign common from the first bracket, we'll have x power n plus under root x power 2n plus 1, and we have this another bracket which gives you the identity of a plus b and a minus b. So if we use the identity, we are going to get keeping minus sign outside, we are going to get x power 2n minus bracket x power 2n plus 1 if you use the identity. So we can see that these two terms are being cancelled and we are getting minus 1 inside the bracket, and there's a minus sign outside the bracket, so we are going to get plus 1 eventually. So this is what we have to prove, that this product is equal to 1. Now the other way could be if you multiply the denominator here, this denominator, by its conjugate. So this would be 1 over x power n minus x power 2n plus 1 under root. You should multiply by x power n plus x power 2n plus 1 under root x power n, and divide by x power n plus under root x power 2n plus 1. If you expand this, if you use the identity, the a plus b, a minus b in the denominator, you are going to prove that the two sides are equal. So this could be the other way. Now in part B, you have to use the method of differences, but before we use the method of differences, we have to write the un term. So the un is going to be, the first part is this, which is x to the power n plus 1 plus under root x power 2n plus 2 plus 1. And now this part can be replaced with the other side we have proved in part 1, with the right side of our proof. So here we can write minus x power n minus root x power 2n plus 1. So this we are going to use in method of differences. So for n equals to 1, when we plug in n equals to 1, we are going to get x power 2 plus x power, when we plug in n equals to 1, we are going to get x power 4 plus 1 under root minus x power 1 minus x power 2 plus 1 under root. When we plug in n equals to 2, we'll get x power 3 plus x power 6 plus 1 under root minus x power 2 under root x power 4 plus 1. Similarly, if we keep doing that, we are going to get the n equals to n, and this will be x power n plus 1 plus x power 2n plus 2 plus 1 minus x power n minus x power 2n plus 1 under root. So we see the terms are being cancelled. So this entire term will be cancelled with its second term in this second row. That means this term, the first term in the second row, will be cancelled with the second term in the third row. This sequence will continue, and the last term will be cancelled with its first term in the second last row. So finally what we are going to get, the sum of this un, from n equals to 1 to capital N. This is going to be, we have to plug in capital N here. In fact, this is capital N. So I'm going to write this here. It was capital N everywhere. So the sum of un is going to be, so the term we are left with is this part and this part. So the un term is going to be x to the power n plus 1 plus under root x to the power of 2n plus 2 plus 1 and minus x and minus root x square plus 1. This is the sum of the un from n equals to 1 to capital N in terms of n and x. Now in part C they are saying deduce the set of values of x for which the infinite series where the terms are being added. So these are not numerical terms, these terms are in terms of x. So it's written in the general form u1 plus u2 plus u3 up to so on till infinity. That's what they mean. So this means we are going to add from n equals to 1 till infinity un, all these terms we have to add. So they're asking you to write down the set of values of x for which this infinite series is convergent. So this is convergent. So if it is convergent, we have to check the x power. If we check the term here, it's x power n plus 1, it's x power 2n plus 1. So if it is going till infinity, this n will be replaced with infinity. So we are going to get the term x to the power infinity plus 1, one of the term, and the other term is going to be x to the power 2 times of infinity plus 2. Now this entire sum will be convergent only if we have the x value between minus 1 and 1, because whenever you have a value, say I take for example 0.5, it is raised to the power of infinity or infinity plus something which is still infinity, or infinity times 2, infinity times 2 plus 2 will still be infinity. This will vanish or get to 0 only if the values are between minus 1 and 1 but not 0. If the value of x is more than 1, say 2, and 2 raised to the power infinity is divergent. So if it is convergent, x must be in this range from minus 1 to 1, and obviously is not equals to 0. So this is the answer of the first part of the question. The set of values of x for which the infinite series is convergent, and give this sum to infinity when this exists. So we have to go back to the summation formula. It's the from n1 to capital N un equals to, so if we plug in, if we apply the limit here, that will become 0. The other part will become 0, and here is x and root x square plus 1. If we simplify, this is our answer. So it's 1 minus x minus root x square plus 1. This is the sum when n tends to infinity. Sum of the terms of the series un when n tends to infinity.